Hi, this is Professor Fernandez, and this is the video 2 of lesson 4. We're talking about the existence of one-sided limits here. This example is from Calculus Simplified. So let's look at this example. It's example 4, the fourth example in chapter 2. So what does it say? It says use the graph to evaluate the function f of x graphed in the figure, and use the graph to evaluate the limits, right, over here, 5 limits, based on the graph we're given. Great, so let's look at the limits that we are given. So all of these limits, because we're talking about one-sided limits, right, are one-sided limits. So I just want to point that out over here. And again, in the previous video, video 4.1, you might want to review that. So just to get a sense of what the notation looks like, review of one-sided limits. As a very quick sort of 10-second review, I'll zoom in here. This means approach x equals -2 from the left. Okay, that's what this tells you over here. This means, for example, approach x equals -1 from the right. Okay, so from that direction. Very quick little review again. So I highly suggest you check out that video if you want much more details about one-sided limits. The topic of this particular video is the existence of one-sided limits. Okay. So one-sided limits, just like any other limit, don't always exist. Okay, they are limits, so we are looking for the trend in the f of x values as x approaches a particular number from a particular direction. That trend in y values might not yield a numerical value like 10, okay, or it might not be possible to evaluate that trend. So these are just verbally me vocalizing to you some of the ways in which a limit might fail to exist. So now let's go ahead and investigate these limits so we can see some of that. So let's take this first one. We are approaching -2, x equals -2 from the left. So we're going to go to our graph, okay? Here's -2, and I'm going to look for the portion of the graph that is to the left of -2. And I notice that I don't know. There is no information that's given to me about the graph to the left of -2. So we can call the outcome here, we can classify it in various ways. But I am going to write D and E, does not exist. Okay. If there were another category that calculus instructors use, I might propose something like there's just not enough information given to us for us to be able to investigate this limit, because that's exactly what's happening here. I don't know what the graph is to the left of -2, so I cannot assess what the y values tend to as x approaches -2 from the left. Okay, but I'm still going to just refer to it as D and E does not exist. All right, how about -1? X equals -1, and I'm going to approach here from the right. So I'm going to find -1 on the x-axis. Here it is. And I'm approaching from the right. So I only care about the portion of the graph that's to the right of -1. And I'm going to do the same dance as before. I'll start a little bit to the right of -1, and I'll start approaching, and I'm going to track where the y values are getting close to. Right? The y values seem to be decreasing toward -1. So that is my limit. Right? So that this limit is equal to -1. Like we talked about in the previous video, video 4.1, it does not matter for the purposes of finding a limit whether this circle here is open or closed. This closed circle tells me that the point -1, 1 is a point on the graph, right? At x equals -1, the y value of the function is 1. This down here tells me that at x equals -1, the y value is not -1. But it turns out that in terms of the limit, that is the number, -1, that the function is approaching as x goes to -1 from the right. Okay, so now we'll switch over here and let's talk about this limit. So we are now approaching 2, and we're doing it from the left-hand side. So I'm going to go over and find 2 on the x-axis. So there it is, and I'm going to approach from the right. So I'm going to look at just the portion to the right of x equals 2 on the graph, and then try to see what's going on there. Notice that the graph seems to be shooting off to positive infinity, right? This vertical asymptote is reminding us that the graph is shooting off to positive infinity there. So I'm going to write one thing here that may be at odds with perhaps if you've already taken or currently in a calculus class. I am going to write does not exist. And then I'll write in parentheses positive infinity. Some calculus instructors might write something different. They might say that this limit equals infinity. I find, and I say this in the book, that it's confusing for many students, perhaps even most students, to see this even written down. And it always causes a lot of conversations, useful ones, but still points of confusion for a student to see an equal sign and then the symbol infinity. Because, we instructors tell you all the time, infinity is not a number. It is more of an idea than it is anything else. And we're used to using equals for various numbers in calculus. Later on, in other fields of math, we use equals a bit more sparingly. So perhaps this is one good reason to, start doing this at this point in your math education. But I prefer to just call it what it is, right? The idea of a limit is what are the y values, the f of x values, tending to as x approaches this number from a specific direction. For this graph, the answer is the y values are just racing off to infinity. So there is no number that the y values are approaching, right? So this limit does not exist. However, there is information that we can give you. It not only does not exist, it does not exist for a different reason than this limit did not exist. Remember, this is the limit where we just did not have information from the graph to the left of -2 to be able to investigate the limit. This limit also does not exist, but we do have information that can tell us what's happening. That's the information right here. The graph is racing off to positive infinity. So this is the notation I prefer. Again, your calculus instructor might have you prefer to write something like equals infinity, but they both mean the same thing, that the y values are getting larger and larger and larger without bound as x approaches this number in this direction. Okay, how about this next limit? So what are we doing here? We're looking at x approaching 3 and then from the right. So let's go on our x-axis, clear some of this clutter. Find x equals 3, here it is. We're approaching from the right over here. So I'm only looking at the portion of the graph to the right of x equals 3. Again, as I've said in the previous video, I'm not counting that as to the right because that is actually at 3. And once again, the limits care about what the y values tend to as x approaches 3, in this case from the right, not the y value at x equals 3. That would just be f of 3. That would be the y value at x equals 3. So that's not what we're calculating with the limit. Okay, so looking at the graph here, if we start marching from on the graph toward x equals 3 from the right, and then keeping track of the y values, right? It looks like these y values are decreasing toward 1. Okay, so that is our limit. So we're going to write over here, this limit equals 1, so that one was a little faster. And then the last one, how about x approaches 4 from the right? So similar thing I'm going to do here, remove the clutter, and then look at 4 from the right. So first I'll find 4 on the x-axis, so here it is, okay? And then I'm going to look at the portion of the graph to the right of 4. And here I run into the same problem as before, the first limit we investigated. I don't have information about the graph to the right of 4, so I can't investigate this limit. For all I know, it could be 2. For all I know, the graph could be doing this, and the answer could be 5. Could be doing this, and the answer could be 0.5. I have no idea. So for the same reasons as the first limit, I'm going to say that this limit does not exist. So DNE. Okay, so zooming out there, quick little review, right? These are just a few ways that limits can fail to exist. You may have insufficient information to actually investigate or calculate the limit. If later on we'll talk about actually calculating limits using algebraic techniques, for example. You may have a situation where you know what's happening with the y values, they're going off to infinity, but that's not giving you information about a specific number that the y values are approaching. So again, we say the limit does not exist. Or you may be lucky. You may be able to actually determine, as we did in these two examples, a specific number that the y values tend to as x approaches a prescribed c from either direction.